Good morning, everyone. I hope you can hear me. We're going to start our lecture on memory. We're just going to continue from where we stopped last week. But before we start, just wanted to make an announcement. So Maureen told me that you agreed on a date for the exam, and it will be a physical exam, and I think the date is 10th of May. Okay, so that is a Monday. Yeah, 10th of May is a Monday. We'll start at, because that's the day when also the computer engineers are able to do the whole class. We are going to start at 10 here at SEDAT. Now, I've actually wanted to give you a few other assignments, but I've had issues getting those into the system, into Mugume. But we'll continue, and when those come, they'll come and you'll be able to do them. But please prepare for the test. Now, we want to look at some examples of ROMs. So last week we looked at ROM timing. We looked at how read-only memory works. So for instance, the critical inputs were the address inputs and the control inputs, and then you get your data output. I think this is a read operation, mainly because when we are dealing with read-only memory, we are reading. We are not really writing, although that's not a blanket statement, because sometimes we are able to write into ROM. Some of the ROMs that we are going to look at, the number or the frequency of writing is much less than the frequency of reading, and so they are ROMs. So in fact, we're going to find that all semiconductor memory devices where the number of times that you read is more than the number of times that you write, we just tend to call them read-only memories, but it's not true that we never write into ROM. So let's look at some examples. There's the mask programmed read-only memory. This one is, as you can see, it uses some type of transistors as their cells. So you know that a flip-flop is really made up of transistor electronics. So what you have is mask-programmed read-only memory, which we can call EPROM, although they are commonly referred to as ROM, just ROM. So usually when they say ROM, they actually mean EPROM, and we can use the two names as well interchangeably. But you can see here that you have an array of 4 by 4, okay? Meaning that at each of these locations, there is a cell where you can keep a bit of data. And so we have columns. Okay, so we have, these are columns and these are rows. Okay, so we need to be able, and really the columns give you the word, okay, word size. So in this case, the word size is 4, and this is D3, D2, D1, and D0. And so we need to be able to select between the rows, so that when we select row 0, for instance, then the word stored in row 0 can come to the output, okay? Because remember, we are reading once again. Now, how do we select between 4 rows? We can use a decoder, and usually this is a 1 of 4 decoder. 1 of 4 means that one row will be selected out of the 4 possible rows. And if it's a 1 of 4, then its inputs are going to be 2. So A1, A0 can change from 0001, 10 to 11. Okay, so depending on which input you have at the input of the decoder, one of those rows will be high, the other ones will be low. By being high, it means it's been selected. Now, the mask is like a stencil. If you know stencils that we use to write things on, scribble things on some equipment, that stencil is similar to the mask. So you have this substrate, and this is done at the industry, and you pre-select and say that I'm going to store a 1 here, I will store a 0 here, I'll store a 1, and I'll store a 0. Then you give this to the manufacturer, and when they are manufacturing this ROM, they burn that within the memory. It is called burning in. You know, you burn in the data so that all of the time you always have a 1 here, a 0 here, a 1 and a 0 here. And then you could choose that for row 4, you want to have a 1, you want to have a 0 and a 0 and a 0, for instance. And once that is burned into the ROM during manufacture, it will always remain there. You cannot change it. If you want to change the program within that ROM, it means that you have to throw it away and get a new one. You cannot unburn things that have already been burned in the mask programmed read-only memory. So this is what you see here. So for instance, let's say that we have selected row 0. That means row 0 is high, the others are low. If it is high, and then you can see that, I think that's the source, you can see that this terminal is connected to VDD. Okay, I think you know the difference between VDD and VCC. That is connected to VDD. So when this is high, when you have a 1 here, that power is able to cross to the source, to the source terminal. And that source terminal, you can see it is connected, for instance, D3, meaning that D3 now reads it. Actually, D3, there is a potential difference to ground here. So D3 is right above, it is right above that resistor. So by burning in, what we do is on the mask, you can choose to make this a 1, and to make it a 1, it means the connection here is maintained. You can see that connection is maintained, that connection is maintained. If you want to store a 0, this connection will be burned, it will be broken. So that even if you have selected row 3 and it is a 1, meaning that this VDD, you can see it is connected to VDD here, that one, meaning you have VDD here, but it cannot cross, okay, because that is an open circuit. So the power cannot cross, the voltage cannot cross, meaning your D3 would now be 0. Let's see if I can open a new slide and we look at this again, okay. So let us look at what is actually burned within here. If you look at row 0, wait. Yeah, let us look at the decoder. We have A1, A0, and then we look at rows, okay, and we look at the data. And this data is D3, D2, D1, D0. Now, decoder, if it is decoder 00, we have selected row 0. Okay, that is the row that is selected. It means these rows, the other rows are 0. They are low. And if you have a 0 here, we already said that that power cannot cross over that. That's how the transistor will work. But I'm not here to teach transistors, so let's continue with digital electronics. Now, it means that the data that is stored in these transistors, these 4 transistors, will actually move all the way to the output, because these ones will not interfere with that sense power. The power, yes, they have VDD, but actually that VDD cannot cross to that line, right? So it means that if you look at Q naught will be, actually it's, yeah. So Q naught is actually connected to D3, so that's fine. We have a 1, because that is, if this is a high, if you have a high here, this VDD will cross to the source, because that is actually a circuit. That circuit is connected. So you're going to have a 1. This one will always be 0, because VDD will never cross this junction since it is an open circuit. You have a 0 there. Then here you have 1, and then you have 0. Catherine, the difference between VDD and VCC, there is no difference really. It's that it's just the symbolism. So VCC is used in TTL, and when we work with MOS, we usually use VDD. I think everyone should know that. But yeah, that's really, it's a simple difference, but we are, same voltage, really 5 volts. Now, if we look at row, if this was 0, 1, the decoder is going to select row 1, okay, which is that row, which means that this row will be high, okay? So you have a 1, 1, 1, 1. That means that what, and of course this terminal now is connected to VDD, this one, meaning that wherever it is a 1, it will cross over. This power should cross over. Now, in this case at Q4, it will cross over because we have a circuit. So you have a 1, but this is not connected. So a 0, and then a 1. Yes, the VDD will cross over, but you have an open circuit, meaning that the current will actually not cross to come down here. For that 1, 0, we select row 2, and row 2 you can see it's a 1, a 1, a 1, and a 0, 1, 1, 1, 0. And for row 3, we will select that when we have a 1, 1 going into the decoder, meaning we select row 3, and then we would have 0, 1, 1, 1. I don't know. I don't know, because we had this issue last week. Now, when I recorded the video actually and looked at it, it seemed to work. Okay, it seemed to work. So it could be your connection. It could be your individual connection that is giving you problems. I'm not very certain that it is me, that the problem is with me. But if the problem were with me, then I wouldn't be able to solve it anyway. I would probably just have either to stop writing so that I don't confuse you. But the problem is, if I don't stop writing, how do I teach? It is very hard. And so it might be an individual issue. Are there any students that are having a better experience? Yeah. If Sylvia is fine, I see Mary Akelo is fine, then it means that the issue is not here, okay? I would encourage you guys to find places with better networks next time, so that if you are using your phone, that could be an issue, okay? And if you are in a place with with poor network, that could be an issue. So please try and improve the connection at your side. But really, there is nothing I can do. I'm actually at Makerere University connected to Mac Air. Oh, what we've just been doing is actually already here. Now let us look at an example. We can use mask programmable read-only memories to store mathematical functions. So a mathematical function is a function that always gives you the same answer every time. So I know cosine of 45 is whatever, 0.707, or sine of 20 degrees it is always that number. And so you have these mathematical tables or function tables where things always repeat themselves because that's a function. Now, we can use ROM to store such information which never changes. Actually, that is the main application area for ROM, being able to store things that do not necessarily change. Now, you have a function like y is equal to x squared plus 3. How do you store this in ROM? We know that in ROM, we have outputs and we have inputs. And these inputs could be address. Actually, usually what they do is that they make the address input of this ROM the function. You know, when you say fx, okay, you could say y is a function of x. Usually this is the variable. This is the small variable that when it changes, it varies y, basically. So usually the inputs are x and your outputs become y. Because it is y that you want, it is x that you have. Now the inputs are very easy to predict, because those could be like the inputs could be your address bits. So usually, first of all, what you do is, and in fact in the question they say, assume that the input address supplies the value of x and the value of y is the output. Okay, now we can say that let my address is B2. Let address is, for instance, B2, A1, A0, and we know these can change from 00, 01, 10, and 11. So when the address is A1, A0, 00, 01, 10, and 11, sorry, the decimal, you could say the decimal equivalent of this is 0, 1, 2, 3. So what is y? Y is x squared plus 3, but you remember this is x actually. So x squared plus 3, here it will be 3, here it will be 4, because x squared, 1 squared is 1 plus 3 is 4. X squared here is going to be 4 plus 3, 7, and here it will be 9 plus 3, which will be 12. Now, because 12 is, you cannot decode 12 using 3 bits, but you can decode 12 using 4 bits. So then we can say that our output, now this can be 0, 0, 1, 1, meaning we need 4 bits, D3, D2, D1, D0. 4 will be 0, 1, 0, 0. 7 will be 0, 1, 1, 1. And 8, and sorry, 12 will be 1, 1, 0, 0. So this is how you know how you can. Now, it means that every time you give the address as 00, the output will be that data. So the information that is stored at address 00 is that data. The information stored at 01 is that data, and so on and so forth. I just want to help us. I want to see how we can now program our read-only memory, our mask programmed read-only memory. So now I see that, for instance, when I'm doing 00, my output is 00, 1, 1. So for 00, my output is 00, 1, 1, and this is the decoder. Obviously, this is going to be row 0, because if I have my inputs as 00, I'm going to be selecting row 0. So I would break this, because remember this is D3 and that's D0, and this is D3, D0. So D3 needs to be 0 if I select row 0. This I will break, so that's good, it's already broken. This one I'll connect, and that one I will connect. For 01, we have seen that we have 0100, okay? It is 0100, and it is row 1. So for 01, I'm going to select row 1, and I will break that. I will leave this connected. I will break that, and I will also break that, and so on and so forth. For row 3, we have 7. So for row 2, sorry, it is 0, it is 1, 0, row 2. and the data is 0111. So it means I'll break that. I will keep this connected, this keep connected, and keep that connected, and so on and so forth. And so you can see what they program. But the catch is that every time I have programmed this, every time I use it, I know it's almost like you know what you expect because it doesn't change. And so this is the information that has been burned into the ROM, and it will always be the information that is burned in the RAM. Now, sometimes you have a scenario like okay, so let's say my equation was actually y is equal to x cubed plus 2. Okay, x cubed plus 2. I can say a naught, a1, okay, 0, 0, 0, 1, 1, 0, 1, 1. That means my x is actually 0, 1, 2, 3. And my y becomes now 0, not 0, it's actually 2. Because 0 cubed is 0, 2. 1 cubed is 1, 3. 2 cubed is 8, plus 2 is 10. 3 cubed is 27, plus 2 is 29. Now, here you have an issue because whereas this can be decoded using 4 bits, this one requires 5 bits. And so that means that your data here will be D3, D4, D3, D2, D1, D0, okay? And then you can go further and find, you know, so this one will be 0, 0, 0, 1, 0, for instance. 3 will be 0, 0, 0, 1, 1. 10 will be 0, 1, 0, 1, 0. Is it? Yeah, so that's 8 plus 2 is 10. And then 29, which is, yeah, whatever it is. But my point is that depending on the output you get, you need to code it using the right number of binary digits. I've seen in the past where people have taken the example as it is and they think everything must stop at 4. The other thing is that obviously this also, you might ask, why are we always using only 2 input bits? As you can see, the example we've just used requires 2 input bits, and obviously this will give you, it's actually really a 4 by 4 ROM, EPROM. I could have said, what about if I have 16 by 4 EPROM? This, if I've described the memory, that is the one that decides how many inputs. Okay, so that is 1, 1. Yeah, thank you, Maureen. 1, 1, 1. 1, 1, 1, 0, 1. Okay, so you have your table like this. This shouldn't be ambiguous. Okay, let's move on. Now, there is the idea of now, before we move on, actually, let me say something about this. The problem with the mask program is that you create a stencil. So you can do your design here and send your design to China, and you can even send them just a table, a truth table. And then for them, they are going to create for you a mask. The problem with the mask is that it is very expensive. For it alone, it is very expensive to manufacture. And so it only makes sense if you're basically, when they have a mask, then they use it to reproduce many memories, EPROMs. So it makes sense if you're going to produce so many units so that it cuts down on the cost per unit. But if you're going to design an EPROM and produce 5 pieces of memory, then you're going to spend thousands of dollars for just 5 pieces of memory. And so to alleviate that problem, they came up with a ROM that is called Programmable ROM. It is almost like EPROM. The only difference between EPROM and PROM is that EPROM is is programmed by the manufacturer at the manufacturing stage, and the PROM is programmed by you. So what they do is that they create the same kind of setup, but here they put fusible connections. They put like a fuse. All right. Now you know a fuse, how it works. They put a thin wire, and so you can burn it or you can leave it. That means that they put a fuse, okay, instead of having a very solid connection. And when you go, and then they manufacture those things, and so many people buy them, you know, anywhere, from anywhere, any part of the world. That makes sense to the manufacturer because they can make that and sell to everyone. The problem with EPROM is that it's you, the customer, that gives your own design. Your own design may not be of interest to somebody elsewhere. It means it's only serving you because it is specific to your needs. This one, they create the whole template and they leave fusible links at every node. Okay, so all these would be fusible nodes, fusible links. And what you do is, once you do your program, you reach your lab, you choose which one to blow and which one not to blow. If you choose to blow this one, it will always store binary 0. If you choose to leave this one, it will always store binary 1. But you do this in your own lab, or maybe you have some specialized equipment that can allow you to do this. So you can ask the manufacturer to blow them for you, but they will obviously charge you for that service. Now, this is called programmable ROM. The only difference with the PROM, with the EPROM, is that this one is you do it yourself. So they manufacture these and people pick them and go and program them according to their own needs. However, once a PROM has been programmed, it cannot be erased. You cannot go back and reprogram, because once you blow a fuse, you have blown it. You cannot unblow it. You cannot put it back. And so, but this really alleviates the issue of having a huge cost on an individual, because now the manufacturer will manufacture many of these because they can serve many people out there. And then each unit will be a lower cost if you are buying fewer pieces, for instance. That is a programmable read-only memory. If you want to change the memory that you burned into that program, into that chip, you have got to buy a new chip. You cannot reprogram it. The weaknesses, obviously, of these two, and you can go and see how they actually program these. So you'll be reading the theory. There's a lot of theory around this about how they program it. These things are very difficult to bring, but I usually bring a few bits and pieces in the objectives. So I would say that you should try to read through the notes and try to understand enough to pass. The way that they tried to solve these issues of not being able to reprogram was to create an erasable programmable read-only memory. So it means you can program it yourself, but there is the concept of erasable. You can erase. So this one wouldn't use fusible links, because if you have blown a link, you cannot recreate it. It is not going to work like that. So you can read about the theory of this to see how are they able to reprogram this. But actually, it's that they capture some charge somewhere, and then they can release it and change the cells where they put back that charge. So you can go and read that, and you can see they use ultraviolet erasing. So you just expose this to some ultraviolet signal, which erases everything, and you reprogram afresh. I'm actually more interested, and now you can see this one has two input voltages. This is for normal operation, VCC, meaning this is TTL, and VPP is for programming. So when you are going to program, you use VPP. Usually VPP is higher voltage, like 12.5, sometimes even 21 volts. Whereas for VCC, we know is 5 volts. That's for normal operation. Let us look at let us look at how this would work. First of all, it has 3 control inputs. It has the programming input. So if you're going to program, you need to make this a 0. As you can see, it's active low. This is always going to be high until you are going to program. By programming, I mean maybe you have erased it and you are going to reprogram the memory or the data that is kept within that ROM. You have the chip enable. Chip enable, you know what it does. Actually, the chip deselects the whole thing. It can, if your chip enable is low, it means the chip is selected. If the chip enable is high, in other words, it's inactive, the chip is deselected. So everything inside there just goes to sleep. And when the chip is deselected, it is in a, what we call a low power mode. It consumes very low power, mode. So actually this chip enable is really good when we start to combine them to create bigger memory. So we are going to see that in the next few lectures. But it is an important input that you'll find a lot with memory devices. Now the output enable is like going to manage only the output buffers. If my output enable is 0, it means my output nodes are not in high Z state. If it is 1, that means I've put my output terminals in the high Z state, and they are not going to work for you. If you're reading, remember we are reading with the ROM. The information will not reach the bus for the CPU to pick it up because the outputs are in high Z state. So if you are looking at these control terminals or control inputs, you would say that the program or programming input is always high until you're programming, then you need to put it low. The chip enable clearly supersedes the output enable. The output enable only works on the outputs, on the buffers, whereas the chip enable can select or deselect the whole chip. Okay, so that is really critical. And as you can see, this is 8K. And 8K memory cells, that's 2 to power 13. 2 to power 13 is 8K 8192, I think 8192 or something like that. So that's why we have address inputs from A0 to A12. Those are 13 different, and the 8 obviously are on the output. If you look at this, if we are reading, this is the normal operation. We need to, first of all, select our chip. So C is 0. We need to enable the output, okay, because we are reading, so the outputs need to work. And then we don't need to be programming, so that's always high. We are using normal VCC 0 to 5, and we will get our data at the output. If you are disabling the output, everything is the same, but the output enable is high. If it is high, it will be disabled because it is active low, and then your outputs will be in the high Z state. In standby mode, the one I talked about, the low power mode is also called standby mode, the chip enable will be high. If the chip enable is high, we don't care what these are, but the outputs will definitely be in the high Z state. When we want to program, we need to select our chip. We also need to switch off the terminals actually, because now the output is not necessary since we are programming. And so that's a 1, and obviously program is 0, and you can see we program at a higher voltage, and then we have our input, our data input. If we want to verify what you have programmed, you need to be reading from the memory, and so this is the reading command, but you still do it at a higher voltage. Ellen Nakasoma, back to EPROM, how do we choose input addresses? Actually, input, I sort of talked about it actually. So here, input addresses, we can see there are 2, just 2 input addresses, which is A1, A0. And these will you obviously change from 00 all the way to 11. I said that the reason is because we are basing our example on this scenario where the number of bits are 4, but the number of words are also 4. So word 1, word 2, word 3, word 4. And if you are looking at 4 words, you need 2 bits for addresses. However, if we had like 16 by 4, for instance, then we would need 4 address bits. And then your table would be from 000 all the way to 1111. I hope that that answers your question. Yes, on the program, so the programming is actually this one. When I receive my chip, obviously you're going to have another one, maybe like that. Let's say we are drawing our, okay, this is VDD, and then, you know, it comes with a fusible link. Before that, the manufacturer was either blowing this for you or keeping it intact. But now, all these nodes have these fusible links, and it is up to you to blow whichever ones you want to blow and keep the others intact. If you want to keep a 0 in a certain cell, you have to blow that. If you want to keep a 1, you leave it intact. So the process of programming is really choosing and implementing by storing a 0 in a certain memory cell or a 1 in a certain memory cell. So if I come here and I want a 1 here, I leave that intact. If I want a 0 here, I blow it. If I want a 1 here, I leave it intact. That is really the process of programming. Another question, throw some more light on EPROM operation. The EPROM, erasable. No more light, you'll find it from the books. But what I said is that with the EPROM, you're able to erase the whole memory and reprogram it. That means that you do not have fusible links, because we say that if you blow a fuse, you cannot reconnect it. So the point of erase, you see, erasing would be like going back to the original state and reprogramming afresh. We would not be able to do that if we had fuses. And so it is very, I think, easy to infer that you would not have fusible links similar to like MROM or PROM in an EPROM. However, I say that you should go and see how they store either a 1 or a 0 and are able to erase that using UV light. You expose the memory to UV light and it erases that, and you can reprogram afresh. I think it would be the same. A fusible link, a melting link, because usually when a fusible link means that you have a fuse. So if you look in your plug at home, or the plug in your laptop, there's a fuse that connects 2 terminals. That's a fusible link. If there's a problem with power, if it is an overvoltage, it will blow so that it protects the rest of whatever is behind it. And so I think melting, I've never really had the term melting link, but usually when we have a fusible link, we can melt it, and then we have an open circuit. So it sounds like it would be the same, Arvin. Now we have another one. The problem with the EPROM is that for you to reprogram it, you must get it off the circuit and go and reprogram it separately. You cannot reprogram it within the circuit. What I mean is, imagine you have a motherboard and it has many circuits, and you would need to take off that EPROM, take it elsewhere, reprogram it, and bring it back and put it back on your motherboard. But the reprogramming is very quick. The erasure is very quick and the reprogramming is very quick. You'll get to know more about this. Now we have an electrically erasable PROM. That is called EEPROM, electrically erasable PROM. The erasable PROM, before we saw, it was being erased using UV light, UV ultraviolet light. Now the electrically erasable PROM is erased using electrical means. You don't need some external light source to do that. You can use some electrical means to erase it. Now the advantage of that is that you don't need to take it out of the circuit to erase it. It can be erased in a circuit. That is a big advantage. The problem with it is that the erasure takes longer. Okay, it is a longer process. And so also they are really a bit, because now with the electrical erasure, to be able to erase the EEPROM using electrical means, it means you need some more circuits that perform that erasure, and that's usually within the PROM. And so you find that the substrate becomes bigger. So for the same capacity, the EEPROM tends to be bigger in footprint or in size, physical size, than the EPROM. And because of that, much as the EEPROM sounds like it's better in terms of being able to erase within circuit and so on, the disadvantages are it is slow in erasing, and also it is bigger. You tend to have a bigger substrate because there are other circuits that come with that. Because of that reason, it hasn't managed to overtake the EPROM the way it was meant to be. Okay, because it was meant to overtake the EPROM and bring those advantages, but because of its big size, it hasn't so much as taken over completely. However, it has its own advantages as well. Now you see you have 8K, meaning you have your 13 address bits. You have your control inputs, output enable, chip enable, and write, read, write. You can see that this is WE, meaning sometimes we read. In fact, this is 1. So usually because usually this terminal is kept high, okay, so that we are reading because it's a ROM. And we only put it down, we switch it down when we are going to write. Okay, so write enable. So that terminal connect, these are the 3 control inputs. CE determines whether we are in a standby or low power mode or in normal operation mode by selecting that. So chip enable, you select by putting it to 0, and then you have your output enable, which is also going to control the outputs. Now, we have these interesting terminals here. These are called, when you see IO, it is input output terminal. It means you can use the same terminal for input as for output. And the good thing with this is that because it is electrically erasable, you can, now when you are going to burn data, you can just pass it through the same terminals. But we've seen that these 2 operations cannot happen at the same time. So you cannot really be trying to write and you are reading at the same time. So information is never going to interfere on those bus links. Nansamba Rachel, I'm once again happy to explain this last time. Maybe you may have dodged the class before, but we say 8K by 8. This is the word length. We are not interested in this word length. This is the number of words, and each word needs its own unique address. These are number of words. So if we have 8K words, each word needs a unique address. We need to find enough address to uniquely identify 8K words. 8K is really, 8 is 2 to the power 3. It is 8 times K, okay? And we know that K is 10, 2 to the power 10. So this is 2 to the power 13. That's how we know that the number of bits per address is 13 bits. So you can see that this is really pretty much the same table. We are not going to dwell on it. Let's look at some timing diagram for EE operation. We start at T1, time T1. At time T1, we want to write, because remember, usually we are reading, but now we want to program, okay? So this is the programming operation. So first of all, you give the address at this time, the new address where you want to write. And then, you know, we usually leave a small time for the address to be stable, because you know, if it was a 0 and it's turning to a 1, it needs to shift up to something beyond the halfway mark for it to stabilize within its new state. Now we need to enable the chip, and we also need to give the write enable. The output enable will still be 1 because we are writing, we are not reading, so we don't care about the output. Now the data IO, in fact, in this case, it will be data in, because we are feeding the data that we want to write into the memory. So when the chip enable has gone to a low and our write enable is also low, at some point we give the data that we want to write into that memory. And after some time, we can disable the write enable again and disable the chip. Maybe we can disable or deselect the chip, or we can keep it. You know, this could continue at 0. It doesn't matter. But at some point, we need to stop the writing. However, this is enough time for the memory, for this information here to be written into that address there. That's why you see they overlap. But if we are not going to continue reading or writing, Then usually you put the chip in standby mode, and by standby mode we mean you take the chip back to 0. So the information will be written into that address. Maybe at some point we want to read or we want to write. I think these timing diagrams now are quite second nature to you. Today we may just do 1 hour because I'm so busy trying to do some stuff. So we might do 1 hour of lecture, but that's okay. We've already covered more than 70% of the course, so we are well on our way. Now let us look at another interesting read-only memory, the CD-ROM. This is the one we were talking about last week, although we said that for some CD-ROMs, they are rewritable, meaning that they are not going to probably use this technology. Okay. Now with the CD-ROM, you can see they use a very shiny surface, very shiny and very smooth. And then let me try to draw a ROM, a CD-ROM, you know. And then what they do is when you are writing, you use a laser. And you on each spot. So this, if you were to blow up something, there are going to be certain spots, maybe a certain distance apart from each other. And for each of these spots, you are going to make it either a 0 or a 1. You make it a 0, you know, you make it a 1 by digging a little pit. By digging, I mean you put a high-powered laser that burns that area and creates a small pit. A pit is like a small depression. And so here I've stored 1. Maybe in the next spot, I don't do anything. But when I'm reading, I will read that as a 0. In the next spot, I put another pit. That's a 1. So in this spot, I've put a 0. That will be a 1. If I dig another pit, that's a 1. And another pit, that's another 1. And then I jump there, that's a 0. I jump, that's a 0. So where there's this little dot, just imagine that the laser did not dig. That's because it wants to put a 0. And it will, this data will be written in a spiral fashion, okay, all around the disk. Now that is during writing, you use a high-powered laser. During reading, you use a low-power laser. Now this power laser, what it does is that it obviously has a source of light, but very low power light. And when the light goes into the depression, the reflected light is different from the reflection from a surface that was not that was storing a 0, in meaning it didn't have a pit. And that's how the reader is able to tell based on that reflection what is stored at a 0, what is stored at a pit, what is stored at a place with no pit. And then you're able to get your data back. But once you have already dug pits in these places, you cannot really remove the pits. You have got to that's why it is read-only memory. You can't really reprogram it. And so I want to give you an assignment, a small assignment, really for your own personal interest, that you go and find out how different the rewritable CD-ROMs are. How are they programmed? Okay, I'm giving you that as an assignment before you ask me. Finally, on ROMs, finally, we have flash memory. I think the idea of flash is that it's fast. You know, I think this came from the cartoon, not the cartoon, the superhero. I guess they are cartoons as well. But with flash memory, you have flash memory is non-volatile, but of course it is ROM, and we know ROM is non-volatile. It is high capacity, high density memory, and it is also low power. It consumes much less power. And now we see flash memory almost everywhere. It's in your phone, it is in the computer, it is the small USB stick that you use is flash memory. In the past, having flash memory was very expensive, but right now we see flash drives of 16, 32 GB, 64 GB, I think even bigger perhaps. So you can see since the book was written today, a lot of improvements have happened to the extent that we are starting to buy 32 GB memory sticks at less than 30K, you know, 30K, that's less than $10. So this memory has become very cheap indeed. And most of it is going to be running now in things like ovens at home and cash machines in the supermarkets and so on. But they work essentially the same way as the other memories that we've seen. When you are programming or when you are writing, you're going to use VPP. When you are reading, you're going to use VCC. It is 32K, so it has 32 times 1024 is 2 to power 5, and this is 2 to power 10. So you have 2 to power 15 is 15 addresses. That is for just to emphasize for the student that was a bit confused. You have your control inputs. They work exactly the same way that we have talked about. And so this table should be very easy for you to understand. Now, the good thing with Flash is that you can erase the whole thing and reprogram it, or you can erase bit by bit. You see, before, those others you would have to erase the whole thing, like the EEPROM. You erase the whole thing and start afresh. Even the EPROM. But perhaps the EEPROM, it's possible to erase certain parts of the memory and only program those. So it's possible. But the flash memory also has the capability that you can erase certain bits of information without erasing the whole thing. We can talk about bulk eraser, or you can talk about more targeted erasure of data, and Flash can support this. If you look at this, this is device complexity and cost. So EEPROMs are costly, but this cost obviously now might be cheaper. Maybe that book was written 8-10 years ago. I have edition 12, so maybe 8 years ago. So EEPROM used to be very expensive and obviously very complex because you have the electronic circuits that enable you to erase within circuit. That's why it's a large physically. However, the advantages are, EPROM and EPROM cannot be erased or reprogrammed. Once you've programmed them the first time, that's it. EPROM, you can use UV light to erase everything, but you would have to reprogram out of circuit. Flash, you can program in circuit, you can electrically erase by sector or in bulk. Okay, the things we've talked about. Whereas this one is also in circuit, but you can erase electrically byte by byte. So you can erase specific pieces one at a time. Before we leave this ROM, what did I want to say about them? There's one thing. Oh, we can also say that these are read mostly memories. Okay, most of the time you are reading, and as opposed to writing. All these can be encompassed under ROM. So really ROMs can be memory devices that are non-volatile and where the number or the frequency of reading is way higher than the frequency of writing. Okay, so but we just generally refer to all of them as RAM. Let's look at some applications, and I think we'll end with these applications. As much as I really want to continue teaching you, I need to take care of some university business. Now, these are things we've already talked about, so we are going to talk about them again. Embedded microcontroller program memory. Most of these electronics usually have a processor, a microprocessor. So the microwave has a processor, a MiFi has a processor, your phone has a processor. These little gadgets, PDAs or Kindles have processors. Some of these are really powerful flash processors. But usually you'll find the modern ones have flash memory. And that processor carries a set of instructions that tell it how to perform. A cache register always does the same thing. It never changes because the program within its memory is the same. Okay, and the microwave also functions exactly the same way. Can you imagine if you told the microwave to start and it can't do it, So it always does the same thing. Data transfer and portability. I think this one is very easy. You're looking at being able to transfer information, for instance, on your flash disk. or putting music on your. In the past, we had Walkmans. You know, a Walkman. If you had a Walkman, you know, you probably from a rich background or you store. But today, you put your music on on your phones. Actually, after Walkmans, people got these. What they called iPods or something. The iPhone little players. But times have changed, and you can see now you can put your music on your phone. But still, even then, it is like transferring. It is storage. It is transfer. Bootstrap memory is interesting. So I think you've heard of the word bootstrap. Now, when you today operating systems like Windows 10 could be 10 GB, maybe more, 16 GB, maybe, I don't know. Now, all that information is not stored when you install an operating system. That information is not stored in ROM, because at the beginning we said ROM is very expensive. It cannot be so available for you to store all those files, and it's not even necessary to store all those files on ROM. So what actually happens is that information, most of those files are stored in auxiliary memory, like on the hard disk. So your computer includes what we call the ROM only stores what we call bootstrap programs. It has a bootstrap program, and that bootstrap program contains the instructions that enable your computer to boot. That's why they call it, you know, my computer is booting. That's what it means. It is because it is running bootstrap memory. And those instructions in bootstrap memory enable the computer to go and fetch information from auxiliary memory wherever that Windows folder is. Usually the Windows folder is on the C, partition. And so it is able to go there, pick the files that it wants in its booting process, but things to do with authentication, security, pins, and these days they even have thumbprints. All that can be stored. All that information, those instructions can be stored within a bootstrap program that is very small and is stored on memory, on ROM. But all these other bulk files that are involved in an operating system will be stored on auxiliary memory. So you can see that ROM is used to store bootstrap programs. Data tables. You know data tables. I think we talked about this. A similar table like the one we just did actually in this course, in this lecture, is a data table. So you can use ROM to store data tables. Data tables store information that doesn't change, never really changes. Then you have data converters. So if I'm converting binary to BCD, it doesn't change. Or if I'm converting decimal to BCD, it never changes. If it is my decimal is 0, I know my BCD is 0000. If my decimal is 9, my BCD will be 1001. If my memory, if my decimal number is 27, I know that my BCD will be, is that 0010, 0111? It is always that. So they create a table, and so you can create your data converter to be able to give you what you're looking for every time you press a certain decimal number. So you can imagine, so for instance, you have a system that is generating bits like a computer, but yet you want to display those bits on a monitor. A monitor uses, say, for example, 7-segment decoders that we looked at, which were display decoders. Then you need, from between your computer output and the display, you need a data converter, because that converter, actually you have binary in here, you have this, you have BCD here. So you need to be able to convert, and this conversion is also the same or every time. So you can use your ROM to do that, to store that conversion. Function generators are interesting, but before we go to function generators, let us look at auxiliary memory. Auxiliary memory is the sense that you can use ROM now to store information the same way you use your hard disk, your auxiliaries. So you can use flash drives. I'm sure you guys store things on flash drives and your movies and stuff. So it's the same thing. Now with the function generator, because the function is the same also, similar to like data conversion, You can use a function generator. You can use ROM to store a function. Let me show you how. I'm going to create a new slide and then put this. And then okay. So now I know that, for instance, my sine function, let us say it is like that. I can take a point here, take a point here, take a point here, and so on. And these are points that I can go and store in my ROM. So maybe this, obviously that's a sine function. Now I can store these. When I come back here, after that, we know that the sine function repeats, it's periodical. So after I get here, I don't need to store any more bits. So I can now decode this one to mean something. Obviously, these are analog values. So we talked about analog to division to digital, no, digital to analog converter, like quantization and so on. So I can give these values. So let's say maybe 0001000 whatever, 000 or 100100, okay, whatever number of bits I want to use, depending on the accuracy I'm looking for. Now, if maybe this is an 8-bit counter, so 2 to the power 8 is, I think 2556. So maybe you have your 256 points if you want a lot of accuracy. Now you use the counter to count through those 256 points. And those 256 points are kept in the sense that maybe in your first, you store that, in the first part of the memory, you store that. In the next level, or in the next register, you store the next point. In the next register, you store the next point, and so on and so forth. So that you will store that register, and then register 1, 2, 3, 4, 5, 6, all the way to that one. And this is your maybe 55th register. So when you clock, you start reading from the first register to the second, to the third, to the fourth, all the way to the last. And then your clock will take you back to the first one. But we know that that is going to be repetitive. The sine wave is periodical, so that's okay. Now you have stored these values, the ones and the zeros, these binary bits, into your ROM. And you can see this ROM is 256 by 8, meaning that each of these points is resolved into 8 bits, and those are stored. Now, every time this counter is going through, you are reading these values, and when they are read, they are put through an 8-bit DAC. A DAC converts the digital signal back to analog, and they are passed through, this is what we call a low-pass filter. Really, that's a low-pass filter. And what does that do? It smoothes this. It removes the breaks. It will smoothen it. So if you had these things, that low-pass filter tends to smooth out those joints and steps and so on. And so you can see that all you need is to keep these points. You can like pre-code your sine wave before, or pre-code it. Coding is like converting your analog to digital, and then store them nicely in some sequence in the ROM so that you're able to read them in that same sequence, and you will generate your sine wave at the output. Okay. So let us look at a sine wave like this. Let's say, for example, that we are storing sine of 0 degrees to 90 degrees. We are going to store these in a 128 by 8 ROM. That means that each degree that we store in this ROM will be coded into 8 bits. Now the 128 is 2 to the power 7. That means we have 128 words. Okay, and so we need 7 addresses. No, we need 7 address bits. A6, A5, A4, A3, A2, A1, A0, from all zeros to all ones. Okay, so that will give you 128, sorry. Now, it means we have 90 degrees over 128 to find the size, the resolution, or the step size. 128, sorry, 90 divided by 128, which is 0.703. So that means that when my A6 to A0 is all 0, okay, I'm looking at the sign of 0 degrees, and I can store that sign, 0. If it is A6 to A0 is maybe 0.000.001, I'm going to be storing information for 0.703 degrees. If it is 0.000.010, I will store for 1.406 degrees, and so on. So for instance, are we storing for 100000? Okay, those are 3 and 7. This is actually 2 to the power 6, which is 64. What we are storing really is 64 times the resolution of 0.703, which is times 64, which is about 45.7 degrees. I don't know why that's the case. 90 divided by 128.7 times, yeah, so about 45.7 degrees. Actually, the one that caters for 45 degrees, which is halfway, is going to be 0, 1, 1, 1, 1, 1, 1, 1. Are those 8? So if these are that, okay, remove that one. Okay, so if you have that, you're going to have 63 times 0.703, which should give you about 45 degrees. Yeah, or 44.2. That's strange. 90 divided by 128 is that, times 63, 44.3. Okay, times 64, it is 45 degrees. I don't know what I had got before. 64 times this sounds to me like it is 45 degrees. Okay, so that's okay. Just give me 1 second. The person has gone off. Okay, so just give me just one moment, a moment. Yeah. Okay, so I'm back. Okay. Yeah. Okay. Yeah. So basically 45 degrees is there at the midpoint, 0, 0. It depends on where you end up, but as we can see, it's about 1, 0, 0, 0, 0, 0, 0. That is relevant. Anyway, so I could ask a question like this. I don't have to bring degrees. I could bring percentages. I could bring, but you can see it really boils down back to resolution and step size and the stuff that we looked at with the DACs and the ADCs. Okay, now we are going to do, I think, this is the, you can see we have started semiconductor RAM. So we are done with ROM, and this slide is semiconductor RAM. And I want us to start here next time because if I need to go. Have a nice day. See you Wednesday. Yeah. Okay. Bye.